Yeah, hello.
Yeah, yes, audible.
Okay, great. Let's just wait for 5 6 minutes. Yeah, people are joining. Guys, let's just wait for 2 3 more minutes and then we'll start with our discussion today. The last time, what we left, okay, we had a great discussion last time, but today we need to finish it um, about how to basically develop understanding and analyze the social networks available with us. Okay, so we are going in sequence of what we we are taught in videos. So we will go in that sequence only. We won't be able. We will be finishing that up. Mm, anyways, uh, let's just wait for 5 more minutes for till 6:15. Until then, I'll just set my piece, iPad up.
Sir, in week seven assignment, the first question, you supervised random walk with restart. What is the restart probability alpha?
Just a second.
Is the
Just a second. I'll open it up. Okay, just a second. Give me a minute. I'll discuss it. Um, yeah, let me share my screen. Is it visible?
yes, sir, yes.
Week 7, week 7 assignment. Week 7 assignment was not prepared by me still. Unsupervised random walk with restart probability, edge strength, topological information, optimization. What do you think is the correct answer?
Third, C, optimization regularizer.
Correct. Just a second. Um, Okay, yeah. So Manjula, hello. Did you
Yes,
did you solve
yes,
this
sir.
assignment?
Yeah, I
Have you s-
solved a little bit.
have you submitted it?
Yes, sir. I have done, but
Okay,
I have some doubts.
okay. Just a second. This is week seven. Week seven is this thing, link prediction thing. Link prediction thing, right? Yeah, link prediction.
In a link prediction, we can predict the missing also and also forecast future links also, right? So the option will be no, right?
Option should be topological information first of all. You think why? Then I'll tell you. I think it should be given in the book clearly. If you have book, right?
Yeah, but then
It's
right,
given in the
have
book.
to do.
Anyways, I'll discuss it.
Using the link prediction, we can predict the missing link, and also we can predict the forecast future link also. But here in the question, they have given that we cannot forecast future link. So the
Which
option
one?
will be no.
No. Acha, you are discussing answers.
Yeah.
No. Arey, don't discuss it right now. Okay, there's still a deadline of 1 day. Okay.
Okay.
I'm just telling you why the correct answer should be this one and not this one. Okay. Don't discuss all questions. We can discuss week 6 if you want. Okay. So in book it's not given. Just a second. It should be given. Supervised random walk formula should be there. There should be alpha. Alpha. Yeah, alpha is there. So in any of the cases, alpha generally means restart probability or whatever it is. In case of say page rank, there's alpha, beta, there's something like that, and that also means some probability. Such if you don't find a link, or some at some random times you start from random nodes like that. So ultimately, this alpha represents something which is contained inside a graph. Okay. Hello. Am I audible?
Yes, sir, audible.
So inside a graph, edge strength, okay, edge strength is inside a graph, but it also contains node information. It also depends on node information, etc. The weight of nodes, many things ultimately. Weight of edges, number of nodes. So topological information contains all of the things about the graph. Optimization is it's not an optimization regularizer because we are not optimizing alpha. We are not optimizing some function using alpha, as in case of say machine learning we use alpha as learning rate. So there it can be considered as optimizer, learning rate, something like that, but here it's not like that. Okay. Hello.
Okay, sir, we'll check again. Sir.
It's not given clearly in the book. Let me check it once again if
Yeah,
it's given or not.
in videos also they are not specifically say about it. So
Week 6, week 7, chapter 6, same test
yeah, it's
state.
okay, sir. You can skip to next. No issue.
No, just clear it. Like, I don't have a lot of things to discuss. I just need to complete that and start something new. So I expected a
Yeah,
few
yeah,
more people to
yeah,
join.
yeah. Whatever you planned, you just execute, sir. No issue.
No, still,
Just
I'll
simply
just check
ask.
it. I because I cannot leave a doubt like that. Now it will just, uh, you know, keep on pondering again and again in my mind. It should be given. It should be given. Let me read. Let me read it. What page? Page number? Where's page? Then it should. Yeah, got it. Page 209. 20211. Edge strength is measured by a subscript w. Okay. Hello.
Yes, sir.
Edge
Audible.
strength is measured by a subscript w, while the equation 6.19 represents vanilla page rank type of thing. So ultimately, it's sort of page rank. If you find an edge, you perform that operation. If you don't find an edge, you use alpha type of thing to jump to a random node. So that is basically restart probability that is dependent on the topology. Why? Because finding an edge or not finding an edge ultimately depends on the topology of the network, not on edge strength, and it does not affect optimization in any way. Okay. Got it? Hello. Okay, cool. Yeah, so we'll discuss it in next this Sunday. Um, week 6. If you want to discuss, we can discuss. Do you have any questions in week 6 assignment? There was a typo. I gave it big clam, but they made a typo making it big claim. So, anyways, it's self clear. It cannot be big claim. Hmm. All questions were easy. Week 6 questions were easy. You can easily find it 3 out of 4, 3 out of 5, 3 out. Wow, because I went to the first. Yeah, so it was 0.75. 3 by 4. Okay. Land index. These all questions you did, right?
Yeah, yes, sir.
Okay. Any
But
doubts
actually, in a Luvian method, which one is overlapping community also detected, right?
Yes.
No,
No. Lovan does not detect overlapping communities. Uh,
but but
See,
in the first one, lecture 5, right? So they have mentioned that fast greedy method and Luvian method. They have explained some graph, but that graph is looking like overlapping also. So I thought that Luvian also overlapping community detection.
let me check. Let me check which graph are you talking about. In videos or book?
Videos.
In videos. Which week? Sorry. Which lecture?
Lecture 5, the first one.
Okay, lecture 5. Okay. Let me check. Okay. This one. This one is not.
Yeah, the community detection, right? Fast greedy algorithm,
Yeah.
and the next is Luvian method.
Yeah, Louvain is next.
So,
Just a second. Let me open Louvain.
like this
This one.
only. This one is look like that overlapping only, right? No,
No,
no.
no, no.
I
Communities
I
are
don't
not
know. Just
overlapping.
thought.
The graph looks overlapping, but communities are not overlapping. Overlapping communities are such that you have hierarchical type of thing. You have one community, then you have another bigger community over that.
Oh,
Okay, so it's type of hierarchical structure. So smaller communities within bigger communities, they are overlapping communities, or say some intersection between communities is present. Okay, so see, these nodes are independent. These are of one community. 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 Okay, it's not like one node is being shared by two communities. It's not like that. Okay, so they are not overlapping at all. They are independent. Yet they are a part of overlapping graph because the graph is not planar. Getting it?
okay. By the result only we can come to know that is not overlapping, right?
Exactly. I mean, just by visualizing, you cannot say that. Ultimately, you have to perform the passes, community aggregation, modular optimization. Then you come to know whether they are overlapping or not. Okay? Mm, okay. So, yeah, that's that. Um,
The Rand index, if it's possible to explain
which week?
shortly.
Which week? Which week?
Yeah, week 6 on lecture 10, I think.
Lecture 10, week 6. Where's lecture 10?
Yeah, week chapter 5.
Oh, this thing.
Yeah.
Okay. So, what is purity measuring here? See,
Yeah.
ground truth community labels. These are ground truth community labels. C. These are the set of predictor community labels. It's defined by intersection. See, what is the maximum? What is maximum? What is maximum? Three communities are there. Okay. Out of four, there is one node. like that. What is this?
Yeah, 4 comma 1 comma 0. That one. From that we are finding out maximum, and
Exactly.
this one is we are calculated the purity.
So this is say dark. This black one is zeroth community. Okay. This one is sorry. This is the first community, and this is the
No,
second.
no.
Sorry. This no sorry
That
nodes.
black is 4, right?
Sorry.
That black color is 4, and
No,
that
four. It's number of
time is
nodes.
1,
No, no, no.
and that
I'm talking about
no.
index. I'm talking about index. Zeroth index is black. First index is this shaded dashed, and this third index, second index is this one, grayish one. Okay, so it's 4 comma 1 comma this thing is not present 0. Then this thing 0 comma 2 comma 3. Then 0 comma 5 comma 1. So that gives us 0.75.
Next.
Okay.
Yes, this I understood.
Okay, let's go
Run.
to rand index. Rand index, where is it?
This one, okay.
This one, right?
Yeah.
So rand index that indicate the nature of decision taken by algorithm. True positive we know, true negative we know. Okay. False
Yeah.
positive is a node is uh, say node is positive but it's falsely predicted. Okay, so it should be the pair of nodes are in different communities.
Is there any shortcut to remember this? This little bit
Shortcuts.
confusing, right?
No, it
This
won't be
true
confused. I'll tell
negative.
you. I'll tell you. I'll tell you. I'll tell you. Okay, just let me open my iPad. This is very easy. Pausing it here, and I'll first tell you the confusion matrix. Do you know confusion matrix?
Yeah.
And do you know
I,
true positive, false positive, etc., etc. Normal.
yeah. If it is a, if I thought the link is there, then if I predict the link should be there, and the output is also there, means that is true positive.
Okay.
So if the link is not there, if I predict the link should not be there, and in the same way the link is not there, then it is true negative, right?
Okay.
Yeah.
Great.
And
The other two cases of false negatives and positives are false.
uh,
I'll explain it anyways. Let's just read it once. A pair of nodes are in the same community in the predicted and ground truth community structures. Okay. A pair of nodes are not in the same community in predicted as well as ground truth. Okay. So basically, you take two nodes, and you check whether they are in same community or not. In ground truth, you take two different nodes randomly. Okay. Hello.
yeah, yeah, yeah,
So
yeah.
say you take two nodes of different communities, and they lie. The algorithm predicts them in the same community. Then through negative case, sorry, yeah, the algorithm presents them in the different communities. Then it's true negative. If you take two nodes from the same community, and algorithm predicts them in the same community. Okay.
No.
Hello. Say, let me just go back here. You
Yeah, yeah,
you
yeah.
take one black node, you take one this shaded node. Okay. Hello.
Yeah, yeah, yeah.
See, so this is the purity. Why the purity is not correct here? Because these things should lie in one community. These all things should lie in one community. This gray should lie in another community. This black should lie in another community. Okay. That's why this is 0.75. This means 75% of the nodes lie in correct communities, while 25% lie in different communities. So this is a very different way of measuring. So if I take two black nodes I take, and if I ask them, sorry, let me just go here. Okay, so they are they are in ground truth. They are in same communities. Okay, algorithm predicts them to be in the same community. Okay, then it's true positive. Then you take one gray node and one black node, and the algorithm predicts them to be in different communities. That is true negative. Um,
Actually, I think
Wait, let me come to this false positive and false negative. Okay? Hello?
Yeah, yeah, yes.
So, false positive means a pair of nodes that have been predicted to be in the positive case falsely. Okay? So, consider two nodes that are in, say, consider a black node, a gray node. They are in different communities. But algorithm predicts them in the same community. This means they have been predicted as positive case, but that is incorrect. Okay,
Okay.
so that's why they are false positive. Similarly, false negative. Take two nodes. Okay, that uh,
See, what I think is,
hello.
so for that community, how we have to identify this true positive, true
Mm,
negative, and all
Let
that.
let me
Either
connect.
single
No. You do it. You
community or through.
let me tell.
Yeah,
Let me open my iPad. Okay, let me connect it, and then I'll tell. Okay. So you are asking how to compute it for all nodes, right?
yeah. So
Uh,
here they have measured, right? Something for three community they have measured, right?
that is basically count. This is basically count. I'll tell you. I'll tell you first generic case, then we will go to
Yeah.
this stuff. Okay, let me open another notebook. Um, okay, so let me take start with two communities only. This is one
Oh, yeah, yeah.
community. It has these three cross nodes, one blank node. Okay,
Yes.
screen is visible, right? Let me check.
Yeah, yes, sir, visible, visible.
Okay, cool. Okay, see. So if I take these two
So
nodes,
now so now the question will be identify the random index for the given community, right?
yes,
So for that we have to take all these two communities.
yes, these two communities you have to take. And how will you do it? You will take counts. See, example is given, right? Example is given in this. See, I'll explain with example.
Your screen is
Oh,
stucking, so
shit.
now
No. I am on my PC right now. Just a second, let me share my screen. Um,
yeah,
Visible?
yeah, yes, yes.
So what does this thing tell you?
Confusing actually. This one is we understood the true positive, that is 4C2 is, that means 4 is correct. So they are telling that 4 edges, right? 4C2, and here 3 is correct, 3C2, or 2 is correct, 2C2, and here 5 is correct, 5C2, and 1C2. And this I understood, and the
Why
next
is it?
thing is,
Okay. Just a second. Relax. Okay. Sorry. Wait a second. Let me just read it. The ground truth committees are marked with three types of shades. Okay. So 4C2. Why is it 4C2 here?
4 is correct, 4 in one group.
In one group, 4 is correct. Then why C2?
That is, everything is connected with every other one.
Exactly. Okay. So then here 3 are correct.
Yeah, 3C2.
Okay. Then here 5 are correct.
Yeah, 5C2.
Then why 2C2?
That here in second community, two nodes are matched.
Exactly.
So,
Exactly. So two nodes are present in one community. So one C2 cannot be performed. That's why these two nodes are not taken.
because as 1C2 is one only, right?
Yes. So anyways, that is useless. So it is 20. Then negative case. Take negative case.
This is confusing actually.
Why is it confusing? See,
Because,
take this shaded node. Okay.
okay,
Okay. Uh, what is this? Yeah.
false negative.
Sorry. Yeah, false negative one.
False.
So 1C1 2C1, then 1C1. No. 3C1. Wait, just a second. Let me just play the video, okay? This is a bit.
It's called false negative in the same community. It's called false positive. What is false negative? False negative is your algorithm assigns X and Y to different communities, assuming that it's a negative pair, but it is false. According to the ground truth, they should be in the same community. It's called false negative. Negative, false, 3 ground truth. Ground truths are negative, false positive, false negative. Let us take an example. Okay? So, the same structure, 3 communities and 3 ground truth. Ground truths are denoted by black, shade and dot. Okay? Let's measure true positive. Remember, we take all pairs, right? So, let's say this community, okay? So, according to the algorithm, so these black nodes are within the same community, and ground truth wise they are same. So, how many pairs are there? There are 4 nodes, right? And these four of them are correct. So, it should be 4 C2 pairs, right? So, 4 C2 pairs are correct here. And you cannot form a pair with this node because this is a single node.
Exactly.
So, here true positive is 4C2. Here true positive is 3C2, 3C2 and 2C2. There. Okay. What's the false negative? So, false negative means what? False negative means nodes are assigned to different communities, but that's wrong. So, say this node and these 2 nodes, they should be together, right? They are assigned in different communities, but they should be together. So, the pairs that we can form out of these 3 nodes would contribute to false negative. So, how many pairs can be possible?
Okay. So false negative is confusing, right?
Yeah.
Okay, let me explain. Actually, I too had a confusion. I had cleared it. Let me share my screen. iPad screen. Hello?
Yeah,
Am I
yes, sir.
audible? Okay, just a second. So see, it had 4 black nodes, one shaded or one gray, one shaded. Then this one had 3 shaded, three black, gray, 2 shaded. Then this one had 5 shaded, yeah, and 1. Okay. So see, these all are black. So false negative is say this node, 2 nodes should be in different communities, but the model has 2 nodes should be in same community, but model has predicted them in different communities. Correct?
Yes.
Somebody is joining. Okay. So what does false negative exactly say? 2 nodes are in same community, but they are predicting in different communities. That's why it's negatively false. Okay. So say this node, uh, this node and these nodes, they should be in same community, but they have been predicted in different communities.
Yes.
Correct?
And in that third community, that 5C also, right?
Wait, let me explain. Okay. So either these nodes should go here. Okay. Or these nodes should come here. Correct? So it should be 1C1 and 2C1 plus either this node should go
2C1,
here
2C1 or 2C2?
2C1 2C1. Why 2C1? We are not connecting them. We are just asking it to move. Unlike true positive, false negative is not about connecting them. It's just determining the correct community for them. Okay? Hello?
Yeah, okay.
Okay? Then either this node can be moved here or these 5 nodes can be moved here. Then again 1C1, 5C1. This should be present. C. Okay?
Okay.
Then third case is um, 2C1, 5C1. Yeah, okay. Either these 2 nodes can be moved here or these 5 nodes can be moved here. These 5 nodes can be moved here. Then it will be 2C1 and 5C1. Correct?
Yeah. Yes.
Okay. Then what is the last thing?
That 1C1, 5C1, right?
3C1. See,
Yeah.
black
that-
nodes black nodes are already contained in one community. We don't have to worry about them. Okay.
Yeah.
We have done everything for these shaded nodes. Sorry, shaded nodes. Now these gray nodes are remaining. These 3 gray nodes here and 1 gray node here. So either this node can be moved here or these nodes can be moved here. So it will be 1C1, 3C1.
Yeah.
Got it? So that is how you compute false negatives. That true positive, okay, and false positive. False positive is what?
So it is wrongly placed in another community that we
Exactly.
have to join and we have to predict that.
Exactly. So basically the rest of the calculations are simple if you can
Yeah.
solve them. Okay.
But why this is NC2, here it is NC1?
So being a part of community means true positive means they are truly predicted. Okay. So this means there exists an edge between them. So you can if you have selected one node, this one pair. See, if you selected this node here and you've taken this node, then when counting this node, you don't want to count this node. Okay.
Okay.
So that is why 4C2, that is 4 into 3 by 2 into 1. So total number of pairs will be 6 only. You don't want to count an edge twice. Getting it?
Yeah.
Like number of handshakes, na? That type of problem.
Yeah. Handshake problem.
Exactly.
N
So that is NC2 only. If there are 50 people, the number of handshakes will be 50 into 49 by 2. Because if A has shaken hand with V, then B will not shake hand again with A. So that thing is done, that's why it is getting divided by 2.
Yeah.
Okay? So yeah, that's that. Any other doubts? Hello?
Yeah. In week 7, third question you see, no? Third question.
Assignment?
Yeah. If possible.
Still I cannot discuss it. But anyways,
But just you can tell, I'll tell. So actual AL is true positive, right?
yes. Actual positive links are AB, BC, CD. Actual negative links are AD, AC and BD. Then predicted positive links are AB, BC and BD, while predicted negative links are AD, AC and CD. So So there's one wrong in both of the cases. What is the
Yeah,
accuracy of the system?
so true positive is 2, right?
True
True
positive.
positive is 2, true negative is 2, and false positive is 1, and false negative is 1.
Yes.
So the answer is 4 divided by 6, right?
It should be. Just a second. Is my screen, what screen is visible? iPad is visible, or just a second. Uh, this is the only problem. I need to change my screen again and again.
Screen stuck, I think.
Stuck. Just a second. Visible now?
Yeah.
Okay. So see, this is correct, 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 this is correct. Okay, one is incorrect. So when you compute accuracy of a system, right? So accuracy is computed for both positive and negative separately. What you are trying to compute is not actual accuracy. What you are doing is now you are putting 4 by 6, correct? Hello?
Yeah, yes.
4 by 6, you are saying, okay, 4, 2 these are correct, 2 these are correct. Who's joining? Okay. So what you are saying is, these 2 are correct, and then these
Yeah.
2 are correct. That is 4 out of 6. Okay.
Yeah.
But what is the problem with this thing?
What is the accuracy of the system? So accuracy is true positive plus true negative divided by that true positive, true negative, false positive, false negative.
Is
Right?
it so? Where is it given like that? Where is this given? Is it given
Yeah,
some?
accuracy, the formula given. Right?
Which one? Where? Which lecture? I think it should be in. Let me check. This is week 7, right?
Yeah.
Okay, then chapter 6. Chapter 6. Chapter 6. Okay, yeah, okay. The correct predictions to total number of predictions. So, how many correct predictions are here? Sorry. Where is it? Where is it? Here, no? Assignment. How many correct predictions are here? Hello? Hello?
Yes, sir.
How many? See, let me calculate it. I don't want to do it before the deadline, anyways. Resisting it. I'm resisting the urge
Yeah,
to
it's
do it.
okay, sir. It's okay. Leave it you. Also, whatever you plan, you can take.
Actually, no. I can do it, but the thing is, no, I don't want to do it right now because this
Yeah.
is gonna be uploaded today and the deadline is till tomorrow. So
Yeah.
that
Okay.
is basically sort of exposing the answer before, okay? But anyways,
Yeah.
week 7, fourth question. What probability? Credit closure.
Steady closure actually.
What is DE? DE? DE?
I thought D should be C D E F, right?
Yes. Just a
So
second. Just a second. Oh, let me just check. Okay. Yeah. I I still cannot discuss the answers of these questions.
so
Ganesh.
just you can explain the concept now.
I can, yeah. So I will explain the concept of this question first. Question number 3 first. Okay. So whenever you are computing true positives, how many true positives are there? So, okay. So true positives are total number out of correct out of predictions. How many are actually correct? Correct. Manjula?
Yes, yes.
Okay. So true positives are out of the total, say out of the three predictions, how many are actually correct? So two are actually correct. Then true negatives are again two,
Yes.
correct?
Yes.
Then false positives are, see this is a false positive. Sorry,
Which one?
yeah, C comma D is a false positive. No, so no. BD is negative, but it has been predicted as positive. So there is one false positive, okay, and then there is again one false negative. Am I right?
Yes, yes, sir.
Ganesh, I'll check that question because I have not made this assignment. I'll check it. I'll check it. I'll confirm it with Megha. Give me 2 minutes. Okay. I think there's some figure missing or something. I've just messaged her. Am I? Just a second. I'm not solving it, but let me share my iPad screen. Hmm. Visible? Is it visible? Okay. Uh, uh, so actual positive links and actual negative links, predicted positive link, predicted negative link is given to you, and you have to compute. We have the samples available for actual positive. What is the accuracy of the available system? Okay. Yeah. So if I'm solving it, so true positives. How many positives? True positives are there? There are two true positives, true negatives, and if you solve it, then it's TP plus F. Sorry, TN by summation of all of them. So that will be 2 plus 2 by 6. This should be it. That is 2 by 4 by 6 is 2 by 3. 3 6 are 18, 6 6 6 6. This should be your answer, even though I did it, but I should not have done it. Anyways, uh, Manjula, have I answered this question for you?
Yeah, yes, yes.
Okay. Let me just check Ganesh's question. Okay. So represents the probability of formation of an edge between nodes in an undirected setting. Then, based on triadic closure property, one can hypothesize that. Uh, just a second. Just a second. Let me check. There should be some graph given right here. Hello.
Yes, sir. Yes.
Some graph should have been given here, right?
Yeah.
Actually, there is no graph in the question, sir. The
Exactly.
question itself.
Exactly. I need to message Mega. Just a second. Stay around. Just a second. Just a second. Hold. Okay.
Okay, sir.
हाँ मेगा बिजी है अभी क्या? अभी बिजी है क्या? 2 मिनट के लिए अगर आप पीसी के पास हैं अपने तो एक चीज़ चेक करिए। हाँ हाँ। जो असाइनमेंट वीक 7 का क्वेश्चन 4 देखिए, उसमें कोई ग्राफ मिसिंग है क्या? हाँ। अच्छा, और मेरे को 2022 से इसके फोल्डर्स नहीं दिख रहे, एक बार वो चेक करिए, मेरे को एक्सेस है नहीं है। एक बार चेक करिए, मुझे दिख नहीं रहे हैं। ठीक है। हाँ हाँ हाँ। ओके, एक बार चेक करिएगा। हाँ हाँ। हाँ 22। ठीक है, कर दीजिए एक बार। हाँ। ओके ओके। क्योंकि बहुत बच्चों की क्वेरीज आ रही हैं और लाइव सेशन में बोल रहे हैं कि उसमें कोई ग्राफ है ही नहीं, तो मैं वही चेक कर रहा था। नहीं, मुझे अब 1 मिनट चेक कर रहा हूँ, 1 सेकंड। हम्म हम्म। हाँ वो कर दीजिए एक बार। हाँ हाँ हाँ, पूरा कर दीजिए। हम्म, 1 सेकंड 1 सेकंड। मेल पे। हाँ मेल आ गया। 1 सेकंड। ये अब जैसे अभी कोई असाइनमेंट में एरर अगर आ जाती तो करेक्शन कैसे कराया जाएगा उसका? ओके ओके, मैं भी देख। एक बार चेक करिए। हाँ, कोई एक क्वेश्चन 4 का कुछ दिक्कत है। हाँ हाँ। नहीं नहीं, है क्वेश्चन 4 5 के लिए अब ग्राफ चाहिए है। ये खोलिए 2022 का असाइन 2023 का असाइनमेंट खोलिए, 2023 का असाइनमेंट। वीक 3 खुला है? नहीं, वीक 7, 2023 का वीक 7 खोलिए। ऊपर वाला वो ग्राफ, वो क्वेश्चन 4 5 के लिए मेक यूज़ ऑफ अब ग्राफ है, लेकिन हमने ग्राफ ही नहीं दिया है उसमें। कौन सा चाहिए ना? हाँ हाँ हाँ, एक बार उनको मैसेज कर दीजिएगा क्योंकि बहुत मुझे सॉल्व करने में दिक्कत है, देखा क्या क्वेश्चन है ये, इसमें कुछ समझ भी नहीं आ रहा है। हाँ हाँ, और मैं एक बार कंफर्म चेक कर लेता हूँ, एक सेकेंड। मैट्रिक्स मेजर, व्हाट इज़ द रेंज, नोट्स एक्चुअली बाकी सही है। सर्टेन इंडेक्स, एक्चुअली ग्राफ ना गिवन है। ग्राफ वो क्वेश्चन 8 में दे रखा है हमने। हाँ हाँ, उनको वो, हाँ हाँ हाँ, हम्म। ठीक है ठीक है ठीक है, ओके 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 ओके, ठीक है ठीक है, ओके ठीक है ठीक है ठीक है। ओके ओके, मैं एक वो अनाउंसमेंट या ईमेल कर दूंगा मैं बच्चों को भी, आप एक बार वो करा दीजिए। हाँ, करेक्शन करा दीजिए, करेक्शन करा दीजिए, हाँ हाँ। ओके ओके ओके, वो खुद ही कर देंगे, वो तो अनाउंसमेंट में डाल देते हैं खुद ही। हाँ, ओके ओके ओके, थैंक्स। हाँ बस इतना ही है, बाकी सही है, बाकी सही है। फोल्डर दिख रहा है, दिख रहा है, दिख रहा है, दिख रहा है, ओके ओके, थैंक्स। um so guys, there has been a mistake from, yes, from our end basically. So you see questions 8 to 10 na, you see question 8 to 10, right? Hello?
Hello.
हाँ, Ganesh, see. So
Yes, sir.
this graph for question 8 to 10 is will be used for question 4. This question will be moved here after some time. We are asking them to move it. Okay. So then you can solve it
Okay,
using
sir.
this graph. Okay.
Okay, sir.
Okay, great. So yeah, your question is solved. Sorry about
Sir,
that.
one more question, sir.
Yeah, this one, like, see, Rand index requires ground truths, but they are not labels actually. Let me show you. So it's week 6. This one, right?
Question number 4, sir.
Question 4. Yeah, I just opened this video only. Let me show you the exact confusion behind this question, which a lot of people are facing. Week 6, right?
Yes, sir. Week
Yeah.
6.
Okay. What lecture was that? Lecture? In which lecture is given? Yeah, this one only.
Oh, no.
That the majority is
See. So technically, the ground truth community structure is given to you. There are no labels for that.
So, which means it is tables and ground truths are different, sir.
Yeah, the thing is, labels basically represent, say, if these two lie in same community, okay, that's not a labeling information for that. Question 8. Which week?
Week 6,
Manjula?
Yes, sir.
Which week? Question 8. Week 6.
Yeah.
Answer is
Because
0
you know,
if they are,
modularity of a network with if all the nodes are belong to a single community, then it's one,
modular.
right?
No.
But they are
How is it 1?
single community, right?
Let me solve it. Let me solve it still.
0, 1.
Hello?
Yeah. This one I have doubt. I
I'll do it.
I think it belong to one. If it is not belong to that single community, then it's 0, right? No?
If they don't belong to single community, then it's 0. But there should be some community, right?
Anyway, I will check. So.
Answer is actually conclusion. Just a second. See, this thing, the modularity will be 0 because if every the network is fully connected means every node is connected to every other node. The actual network is exactly as expected in a random network. Therefore, modularity will be 0 because there is no gain from grouping nodes into a single community. Getting it? Ganesh, you can unmute and speak. Like there are not a lot of people. Because reading this is giving me headache. We use modularity for detection of communities with more intra-connected edges than interconnected edges, but in question answer given as permanence, more intra-connected edges. Which question?
Actually, in hello,
Uh-huh.
sir. Actually, in week 6, question number 6, sir.
Question 6. Okay, if a real network has small communities, so yeah, it is permanence only, it's not modularity.
Sir, in question it is mentioned like there are a lot of well-connected intra-edges, na, sir. So in that case, we use modularity. I think so. I mean, as per the lecture, I understand like that, sir. Like when the network or community is having more intra-connected edges and loosely connected loosely connected edges in between community. I think I understand it like we use modularity detection for that, and we use permanence. If we're having like more edges to the outside communities.
Okay, I'll explain in 2-3 lines. Okay, so what happens is modularity has a resolution limit. Okay, modularity cannot detect small, tightly knitted communities, and they generally prefer larger communities for modularity. Modularity is used for larger communities. Okay, so those larger communities are not well connected. Okay, and loosely means this means their communities are like packed together like clusters, and they are loosely connected means the intercluster thing. This is very wide. My hands should be visible on the screen on camera. This gap is wide, but they are tightly knitted. So modularity has very low resolution. Okay, so it cannot detect those communities. That's why permanence is used. Permanence is very sensitive to tightly knitted intra-communities, intra-community structures. Okay,
Okay, sir.
and about that, so this is very confusing because we are not exactly requiring the labels. Had it been given, do we require ground truth communities for rand index measurement?
In machine learning, we treat both as equal, na, sir, like ground truths and ground truth labels.
Yeah, it is rated in machine learning, but we are not doing machine learning. That is why this question is confusing. Actually, the time I took this I took this assignment. Okay, sorry, I made this assignment. Now it was very easy. Like if I just like rand index formula, you can easily see this is true, positive, true, negative. Anybody can say that labels are needed. Correct?
Sure.
But we are not requiring exact labels. We just need communities, exact communities for that. Okay.
Like having the community information can't be treated as ground truths, sir.
It is treated as ground truth community, but not label per se.
Okay, sir. The confusing word here is label itself. Am I right, sir?
Yeah, yeah.
Okay, sir.
Okay. What is
How
model?
it is ground truth community and label is differed?
Label, if I say this node belongs to one community, that node belongs to other community. If I start labeling with community number, okay, we don't have community number here. We're just saying this is clustered information, na? This is clustered. We just know these are clusters. This cluster is one community. This cluster is one community. This cluster is one community. We are not having labels, exact labels. We are just assuming them those communities, and we are applying labels over those communities manually.
Yes, sir. Got my understanding.
Great. Any other doubts? Week 6 was easy. Week 7 is a bit tricky, I guess. Deadline, I think this deadline will be increased for week 7 deadline. I'll request them to increase it. Anyways, for those who have submitted, I don't know if they will reset it or not. Anyways, let's see. Because we make assignments alternate, na, so week 7 is done by Megha. I have done week 8, then week 9 will be done by Megha. So that way. I hope so. So this correction, the Mega has emailed them and they will fix it. Okay, sorry about that. Any other thing? Any other doubts?
No, sir.
Okay, so now we have 1 hour and I'm gonna teach graph machine learning. Are you guys interested in studying how machine learning is applied in graphs? Say yes or no.
Yes, sir.
Okay, so this will be an interactive session. So just
Can you explain some of your work?
my work, it won't be of much use right now. First, let's study today, and then in the next session I'll explain my work. Okay? Because
Some idea of
sorry,
in which way we can think and like that for a research purpose.
I will explain my work first. Let me teach this because without teaching this, you wouldn't get my work exactly.
Yeah, sure.
Um, so, what is basic machine learning? I'm not going into algorithm part. I'm just showing you how the data is processed, how the graph data is processed for machine learning purposes. Okay? How graphs are used in ML. Okay? So in last few weeks, last coming weeks, we will study GNNs, etc., etc. And I'm not going into the depth of those topics, but still I'll just do some stuff here. So first thing is, what can we predict in a graph, for a graph, or from a graph? These three questions we will answer. So in a graph, what can you predict? Say you have an information. This is your graph. I can ask you to predict this user info. Okay, user info like what community is this user in? Okay, first thing I can predict this. Second thing I can predict is positive, negative, blah blah. Say spam. Is this a spam user or not? Okay, so sometimes it may happen that spam users can lie in non-spam communities. So that is why I have separated these two cases. Okay, so third thing is, this is in a graph. In a graph we can predict this. For a graph, we can predict if two graphs have same topology. First of all, we can predict this if two graphs have same topology, or two graphs represent same same community, or say same information. There might be a case, this is an email graph of Google, this is an email graph of Microsoft. So are they email graphs or not? You can basically check the types of graph. Are they of same types? So for a graph we can do this. From a graph we can do this. In a graph we can insert a node. So what we can do is we can predict link prediction. Okay, this is the most commonly used stuff. So Manjula, you're asking what I do. I do link prediction basically. Link prediction for what purposes? Link prediction for expanding the graph. New node comes in, new information comes in. So basically what I'm doing is I'm doing Albert Barabasi thing using machine learning. Okay, so this is what I do. In detail I'll explain it later on, but anyways, so let's start with link prediction problem. because this is most widely used. The rest of the two things generally come inside link prediction. So I'll tell you how. I'll tell you how graph classification is a part of link prediction only. But anyways, just forget about this for now, and let's study link prediction only. Okay. I mean, am I like? Are you guys getting it?
Yes, sir.
Great. Okay, so this is a graph. This is a very weird graph which I have drawn, and now my task is to see where this node will go. Here, or here, or here, or here. I don't know where this node will go. So for that, I need to understand what information do the links of these graphs contain. Correct? Am I right?
Yes, sir.
Manjula, am I right? I need to learn what info does each edge represent. Just a second, I got an email. Okay. What info does each edge represent? Hmm? How do we learn that? So see, I have this edge here. This edge. So how do we learn the feature, the information of this edge? I can learn this information from the connecting nodes. So basically, node information is used to learn edge info. Correct? Till now it's your this might be confusing, but I'll tell you how. Okay. Till now you're getting it right, Ganesh,
Yes, sir. Getting it, sir.
Manjula. She is gone. Okay. Anyways, okay, you're there. So we need node information so that we can transfer this information to edges to learn. But this is very vague statement, and you might think, yeah, what I'm speaking, but it's gonna be quite evident when I teach you how it's done. So what I'll do is I'll just rotate it like this so that the upper part is visible. So now what we do, assume there is a machine learning model. This is a black box model. Okay, this model predicts probability between two nodes. Correct? So how will it predict? So say I have node A, I have node B, I have some feature of node A, I have some feature of node B. These features can be derived using NLP or computer vision or GNN, anything. Okay. What I'll do is I will use a feed forward network. Okay, and I will apply sigmoid function. Sigmoid function will convert this in a range of 0 to 1, and I will 0 to 1 means it has been converted to probability, and I'll apply loss function here. Loss function, say for positive case it should go to 1, for negative case it should go to 0. So what I'll do is if there is an edge between A and B, make it to 1, class 1, else make it to class 0. Just understand it. So there is an edge. Currently there is an edge between A and B, but there is no edge between A and C. So for A and C, if I pass A and C here in this feed forward network, it should give me 0. For A and B, it should give me 1. Correct?
Yes, sir.
Okay. I will tell you how did we choose, how we did choose C and how did we choose B. I'll tell you. But let's assume we know that. Let's assume we know this currently. So what happens is, now things are gonna get interesting. Till now, what we have done, we have done preliminary analysis of the graph, how to process. But now I'll teach you how this is done in machine learning basically. So what you do is you take a graph A, B, C, D, E, F, A, B, E, this, this, okay? So you write how many edges are there. There's edge AB. Edge AB and B are same. I'm not writing it again. BC, CD, DE, DF, BE, and AE. Am I right?
Right, sir.
Okay. So we can simply write node 1, node 2, class like this. Okay. Node 1 is A, node 2 is B, B, C, C, D, D, E, D, F, B, E, A, E. This is class 1, 1, 1, 1, 1, 1, 1. Correct? Now what happens is, you have positive examples, but you need negative examples for model to train, because the model should know, model should create a boundary. Model learns a boundary. These machine learning models, they learn for classification task, they learn a boundary, so that in some part of boundary positive examples lie, some part of boundary negative examples lie. If I use just positive examples, they will not be they will not be able to create a proper boundary, and they might put all the examples in one side, and that boundary, without a boundary, you will always get an output closer to 1. And for even negative cases, because we have not provided sufficient negative data for proper boundary. Okay, assume there is no border between India and Nepal, so you can just go in without any citizenship problem in any country. So people cannot differentiate whether you're a citizen of India or Nepal, like that. So that boundary is must for graph classification. So what you do is you take some n negative examples, n number of negative examples from the graph. So those examples will be some of the edges which are not present. So like edge between A and F is not present, so that will be 0. Edge between D and B is not present, that will be 0. Edge between C and E is not present, that will be 0, and you keep on doing it till you have sufficient number of negative examples. So rule of thumb is, for one positive example there should be some, say 5 to 10 negative examples. This is a rule of thumb in graph machine learning. Okay, so ultimately if you have say 100 edges, then you have 500 negative samples, so you get 600 training data, 600 samples for training. Okay, one more thing you can do is you can basically create some more negative examples, but what you can do is you can reverse, you can switch node A and node B in negative examples. So it's like I can write E and C 0, so that basically increases negative examples, but this generally does not give a lot of advantage to us. That is why we just go with the rule of 1:5. Okay, getting it?
Yes, sir.
Great.
Sir, a small note.
Sorry?
A small note, sir.
So I didn't get you. Hello?
Hello.
Hello? Sorry, my internet actually goes down a bit sometimes.
Sir, in the in the table you mentioned like A, B's, na sir, node names.
Yeah.
Is that node names represent like a semantic representation of or a vector kind of thing, sir, instead of labels?
Just a second. Let me connect my iPad. Okay. Two, 1, 0, go. Okay. Visible? iPad screen.
Yes, sir, visible, sir.
Okay. What was your question?
In the data table you mentioned like labels, na sir, A, B, C, D, like that. Are that the English letter itself, or any kind of vector that is representing A, or any kind of vector that is representing B?
While training, we will be using vectors, but currently I'm just showing. So ultimately, when you will be feeding them in model, now you will be using vector for A and vector for B when you are feeding them in model. And then what you will do is you will put a classifier here and you will check if it's 0 or 1.
Okay, sir, understood, sir.
Okay. So I'm not going into the vector part because there are like multiple methods of computing that vector. You can use natural language processing. If you have say image data, so you will not be able to use BERT model or say NLP methods. You will be using CNN methods to compute the embedding of these vectors ultimately. Okay.
Yes, sir.
So yeah, that's that. And this is how you compute the graph. This is how you compute the graph. Sorry, this is how you generate the training data. This is how you generate the training data from a given graph. Okay. So what is this method of generating training data from a graph called? This is known as self-supervised learning. So in most of the graph machine learning problems, what you do is you do self-supervised learning only. Because you are given a graph, those graphs have some edges. So what you are given edge data like this. You generate positive samples, then you generate negative samples, and you get this training data from given samples. So you're not doing unsupervised learning. You are given some data, so you generated training data from that only. You didn't do manual labor. Okay, so that is why it is called self-supervised learning. Okay.
Yes, sir.
So now you have data, very easy thing. What you can do is generating data is easy. Okay. So next task is how to apply this. Actually, graph machine learning is not always about using GNNs, using GAT, using say GCon, etc. It's not about that. You can use anything. You can use simple neural network, but if the graph data is getting involved, it's known as graph machine learning. I have done like I can show you a paper, say HEF Enquire. Yeah. Let me share my PC screen. Okay, my screen is visible, right?
Right, sir. Visible, sir.
See, this is a graph data. Okay, this is a graph data here. This is a graph data. But what they have used is they have used BERT. They have used BERT here. Okay. See, they have used softmax. They have used BERT. They have used TANH, etc., etc. They have used transformers. They have not used NLP GCN, anything about uh, anything like that to compute this score. All they have used is BERT. Okay. So, but still, this paper comes under graph machine learning. Let me present my iPad again. Okay, so now you have got training data. Next task is I will tell you 2 3 more things. So that is train test split, why this is important. I'll tell you all these things, okay? So the task is now to train this model. Train model. What you do, you feed this data. You already have some embedding here. Say you have this embedding dimension 128, 128. What you do, you concatenate it. Okay, then you apply a 256 dimensional 256 neuron based feed forward network that gives 64 output here. Then again you apply 16 here, and then you get apply this 1, and so ultimate output is your something labeled 1, that is 0 comma 1. It should give 0 comma 1. Okay, so what you do is you start training. Correct?
Right, sir.
You start training. You train on, say, binary cross entropy loss. Okay? Hello?
Yes, sir.
So you train on binary cross entropy loss such that for label 0 you get this thing close to 0. For label 1 you get this thing close to 1. And then while prediction, okay, while prediction you pass 128, 128 two vectors, and you get one dimensional vector. Say you get 0.97, that is close to 1, so we make it class 1 variable, class 1 prediction. Okay, so this is about machine learning, but how do we apply this whole thing in graph? Okay, so first thing, let me tell you how to do train test split. How to check accuracy of model. How to check its accuracy. Okay, so what we do is we do train test split. Okay.
Right, sir.
Just a second, let me have some water. So say you are given this graph here, this graph. So you need some training data. But what else do you want to do? You want to check if inserting a node gives correct location. Okay, so what you do is you remove some of the nodes from this train data. So you cannot the basic idea is you should not remove high degree nodes. If you remove node E, your whole graph will break, the structure will change. So the basic idea while train test split is my screen, just a second, this is a bit slow. Is this whole screen visible?
iPad screen is visible, sir.
Visible, right?
But not as whole.
Now it should be
Like
visible.
only the part of train test split that
Yeah,
don't
yeah.
remove only you can see, sir.
So don't remove high degree nodes. How do you determine high degree nodes? How do you determine what is the actual, degree is high degree for a particular graph? So what you do is you plot a distribution that says these are basically counts. This is a count, and this is degree. Degree 1, degree 2, degree 3, degree 4, degree 5, degree 6, degree 7, degree 8. So say degree 1 nodes are these many high, degree 2 nodes are these many high, degree 3 nodes are these many high, degree 4 nodes are these many high, degree 5 nodes, degree 6, degree 8. Okay, so there is no degree 7 node. Correct? You're able to get this graph?
It's like histogram, sir, right?
Yeah, it's a histogram. But now remember one thing. The the assumption is the assumption in in graph machine learning we take is to keep things simple. To keep things simple, always remove nodes with degree 1. Why is that? Because when you are inserting a node, you are basically taking that query node and you are checking it with respect to all other nodes in the graph. Okay, so this is a basic assumption that it will only get connected to one node. That is why you always remove nodes with degree 1. If you want to connect to two nodes, then that assumption should be clear from start. Okay, otherwise what happens is if I remove a node with degree 2 and if I start connecting it to the graph, what problem will I face is uh, I I will not be able to tell whether this node originally had degree 1 or degree 2 or degree 3. I cannot tell that. Am I right? Because I have removed that node. Am I right, Ganesh?
Yes, sir. Like here we are assuming like we are making this ML model to connect with only one edge currently.
I'll tell you why. I'll tell you why. Okay. So just assume that you always take a graph with degree 1. Sorry, always remove nodes with degree 1. Just assume it for now. I'll tell you why we choose uh, why we apply this condition. Okay. So say in this small graph, say you remove this node from here. Okay. How will you check? How will you remove this node for testing purposes? So your model is trained. So what you will do is, so node A, and say this is node Q. Node Q. So this is A, this is B, this is C, this is D, E, F, G, H. Okay. So what you do is you put node A and node Q in a fully connected network. You get probability 0.97. Okay. Then you put node B. Sorry. Then you put node B and you get probability 0.98. Then you put node C, you get probability 0.74. Then you put node D, which is node D, this is node D. You get probability 0.83. Okay. So what can you tell from this? That correct order should be node B, node A, node D, node C. So B is the highest probability node. So B is the proper connection with node Q. Okay, correct? Ganesh? Hello? Ganesh, am I audible? Hello, Ganesh. Am I audible? Hello?
Hello, sir.
Am I audible?
Hello. Yes, sir.
Okay. So you saw this, you got this. Now why we are doing this thing here? Hello.
Hello, sir.
Just keep yourself unmuted for
Currently, we're having.
unmute.
Okay, sir.
Keep yourself unmuted. Okay. Don't mute. Uh, so you got this. Now why we did this thing?
Sir, actually, the internet connection is unstable, so I cannot see the slide then.
Okay. Okay. Just a second. Just a second. Let me do it again. Screen is visible, right?
Yes, sir, visible, sir.
Okay. So what you do is you take node A, node Q, you get probability 0.97. Then you take node B, you get probability 0.98. Then you take node C, you get probability 0.74. You get node D, you get probability 0.83. So then you rank them. So ranking is B, A, C, D. Correct?
Okay, sir.
So you know like the B is the highest probability node, so you will connect node Q to node B. But you don't know original degree of node Q. You don't know that.
Okay, sir.
Had this node connected like this, if I remove this, you cannot tell the degree of node Q from the node. You cannot tell degree. Can you tell degree? You cannot tell.
Once repeat it again, sir.
Sorry?
Once repeat it again, sir.
I'm saying if say node, let me just make it clean here. So if node Q is here, it is connected to B and F. If I remove this node, you cannot tell what was the degree of node Q. Can you tell?
Right, sir.
So that is why we always remove nodes of degree 1, and we assume that node will always be connected to there will always be one edge from that node to the graph, and that will be the highest rated probability. So that is how you determine.
Understood, sir.
That is why you remove only nodes of this tower, of this bar. Okay, for train test split.
Yes, sir.
So assume you get in future you have this graph here, and you get a node and you want to check. So what you do, you perform it on all nodes in the graph. You perform this you apply this MLP if this fully connected network to all nodes in the graph, and you rank them, and you choose the highest one and you connect it with this highest probability node. So that was our assumption. Assumption was degree 1 nodes will all the coming node degree is 1. That is why we always remove nodes with degree 1, so that we don't have to deal with degree 2 thing, etc, etc. But there is also a scenario that you can learn the degree of nodes. So what you can do is you can just create another training data. Okay, you put node A degree 3, node B degree 4, node C degree 5, node D degree 2, like that. You take a feed forward network of 128, since 128 was the dimension of this thing, you pass it, and ultimately use a regression based model to learn the degree, and you can round off this thing to get degree. Okay, so that way if you predict degree first, say you for node Q, this prediction gave us degree 5. Okay, so what you will do is you will choose top 5 nodes. You will choose top 5 nodes, and you will connect this queue to those top 5 nodes. Okay,
Yes, sir.
So that is the basic of graph machine learning for link prediction. And what we did here, this was node regression, or you can say node ka feature. We are learning node feature here. So feature is its degree, okay? And ultimately you can also apply this thing for node classification. You can use node feature, that this feature can come from graph using GNN, and you can learn the class of node like this. So in link prediction we always input two inputs. In graph prediction, sorry, in node prediction, node classification, we use one input. That is the node feature. Okay.
Sir, isn't it like we are passing the embedding of A as an X and the degree as Y for training purposes?
Yes.
Okay, sir.
This is basic regression thing which you are doing using MLP, using a fully connected network, so feed forward network, anything. So this is very basic. This is very basic graph machine learning which we are doing here. Okay.
Understand, sir.
Okay. So any other questions in this?
No, sir.
Any other doubts in machine learning course or any stuff you want to discuss? We have 5-10 more minutes.
Currently having no doubts, sir.
Acha, you are not in this Google group, right? Let me share
Which
my
group, sir?
screen. You are not here on this Google group.
Yes, sir, I'm there, sir. Ganesh.
So you are
Second one.
okay. You only emailed this thing. Okay. So what happens is, if you have any doubts, so you want your doubts to be discussed. So what you can do is just email me a day before or 2 days before here only in this Google group, and I take up those doubts in this session only, so that the doubts are recorded here for future references. Because this group will be deleted after this NPTEL exam is over. We will not be able to use it, but these videos they will be always posted online, and we can discuss this stuff. Okay.
Okay, sir.
Okay, so we can also see a bit of graph machine learning, but that is irrelevant for now. No, sorry, graph machine learning. We are only discussing that. We can see graph classification. We have seen node regression, link prediction. We can also see graph classification. Um, but let's leave it for the other day. Okay. Any other doubts in the course? Any other things like basics we can discuss? Okay. If you have any other small doubt, anything you want to
Give me a
discuss.
second, sir.
Yeah, sure.
Let me research, sir.
Sorry.
Hello.
Hello.
Yes, sir. Give me a second.
Sure.
Hello, sir.
Hello.
Hello, sir.
Hello. You're audible.
Yes, sir. Like, we need a little overview of modularity and permanence, sir. Like, which metric is used when, like, for which kind of graphs.
So
That,
basic idea is modularity fails. Modularity fails when the graph is closely knitted. In a closely knitted community, if say you have a complete graph, the modularity will fail to detect it because it cannot detect the high resolution setting. In high resolution setting, But permanence is always used for those scenarios when you want to detect communities which are not tightly knitted. Say they are loose communities. Say in case of Twitter. So Twitter communities are closely, sparsely knitted. They are not very closely tied communities. Sparsely, they are very sparse. So you can be following a trend, and you can gain followers from there. You can follow from someone from the hashtags. Okay, so they are not very closely knitted communities. But Facebook communities are closely knitted because you are friends with close people only. You don't randomly send requests to people. So those are closely knitted communities, and their community structure can only be detected using permanence and not modularity. But Twitter, in Twitter case, you can detect it using modularity easily. Okay,
Okay, sir.
and if you want to see, so I can just show you tutorial modularity versus permanence. See this, you search Google. Okay, this is difference between, yeah, you can see this paper. It's actually, this paper is by my supervisor. This is his BTech work. Okay,
Okay, sir.
I know this guy, Sriram Srinivasan. Just a second. Hmm, just a second, hold. I know this guy. Okay. Anyways, so this is TKDD, and TKDD is a very great conference. So this is the first time when permanence was proposed by anyone, and this was the work done by my supervisor. So if you have free time, I would suggest you read this concept 2, concept 1 and 2 here. Okay,
Okay, sir.
and you can just see, like, these are the scoring metrics. Modularity is used to come check the output, etc., etc. This is very great, and this is very good paper. Okay, so just
Okay, sir.
see concept 1 and 2. I'm sharing the link here. Open it. For modularity, I'll show you modularity of a network. You see this paper, this PNAS 2016 paper. Okay, so the formula is same as given in the book, but if you read this stuff in introduction part, you will get to know, and first read this paper and then read this paper, why modularity was succeeded by permanence. Okay,
Okay, sir.
these two papers are really good. Anyone, but because NPTEL is not a platform for basically asking people to read papers, so that's why we avoid doing that here. But anyways, these two papers are really good. Any other stuff you want to ask?
Actually, what we did in this session is link prediction, sir. Like some kind of link prediction with using ML.
Okay, yes, correct.
But in the lectures, they are given like some like theoretical models, sir.
Yeah, that is empirical. That is this, what we did was stochastic link prediction. That is deterministic link prediction, which what we do there. Okay, we predict links. We can actually, in Albert Barabasi model, we are predicting links only. We are taking a node, we are trying to connect it to high degree nodes. So that is also link prediction algorithm only. But I was teaching machine learning because from in coming weeks, this thing will be coming to the session. Okay.
Okay,
So in the videos you will be seeing link prediction, and this then you will be confused why using split, why using stuff like that. So I've explained it in very clear way why Why to split the graph? We are splitting it to check whether the performance is good or not. And why only we split degree 1 nodes? We do that so as to ensure that we only choose the top most prediction for the correct answer. Okay.
Okay.
So yeah, that's that, and that's all for now. If you have any more doubt, just ask me. We have 4 or 5 minutes more.
Currently, there are no doubts. That's
In any of the previous weeks. Okay, yeah, there was there was a question. Let me check. Okay, there was a question. This one. Were you able to solve this?
1 minute. I will take it.
Okay.
No, sir.
Okay. What answer did you mark?
I marked as 3.
3. That is pretty obvious why you did it. Okay, because these doubts come every week. Okay, week 5. But the thing is, people don't ask it. Okay. So what is a K-click? Tell me.
Um, from one node to another node, the shortest path is K.
Shortest path is K. Okay. So you are asked
In
A.
the network.
Yeah. See, you are asked A, B, C, E, F. Node D is not there. Okay. You can use its path, but node D is not a part of click. Okay.
Understood.
So it becomes a K clan or whatever it is. If we remove this edges, it becomes a K clan or whatever it is. Okay. But see, from node A to node E, you can go in shortest distance 2. From node A to C, you can go in shortest distance 2. From C to E, you can go in shortest distance 2. From A to D, you will take 3 steps, but D is not part of that click. So this is not counted, but its path we can use. Okay. From F to C, you can go in 2 steps. From E to C, you can go in 2 steps. So the value of K is 2. Okay.
Okay, sir.
Okay. Any other doubts? Let's see what other doubts are there. Probability of node belonging to giant component. Acha, see this week. See week 4 or week 5 video. This I have explained this very clearly. Okay, if you have this doubt. Okay.
Okay, sir.
So there's this PMR, this sheet is circulated. You go to announcements. No, you go here. You go in NPTL. You come here. Problem solving session July 24. Go to problem solving session. Okay. Open this sheet. Here you will find the week wise videos on YouTube, and this is the drive where we put all the scribes and everything, collab notebooks. So this thing we discussed in iPad, I'll be putting it as scribe like this. Okay.
Okay, sir.
So you can just revisit these videos. These are very nice. We had done a lot of great discussions here.
I will take it, sir.
Okay, sure then. That's all. We'll meet next week. Please bring your doubts next week as well. Next week means this Sunday. I had to shift this session due to some emergency to Tuesday. Otherwise, we would be meeting on Sunday. I know that's why the people have not joined, because their schedule got disturbed. But anyways, I apologize for that, and it won't. I will try it. It doesn't happen. The session will always remain on Sunday 6 to 8. Okay. Cool then.
Okay, sir.
Chalo, thanks a lot. Bye bye.
Bye, sir.